Yeah, so for this one, right now, this can be a little bit more exercise. And again, this is a rigid. So what you're going to do is this. Right now, say this is the our degree of freedom is theta here. Okay. So here we want to describe the KEQ. That means 1 KEQ theta square equal to. So from here, how many spring elements? 1, 2, 3, 4, 5. Okay, so here we can assume we follow on the designated directions. So that means this bar is rigid, and this length is rigid. So once this rotates a little bit, this is going to tilt it to here as a straight line. Okay, so again, this is the first step, and so in this way you can see taking the free body diagram. So right now I'm taking the free body diagram of this bar. So from this point here, the spring has been compressed. So the spring is going to push back and to recover. And the second one, the spring is going to push back. Okay. This one, this spring has been stretched. So the spring is going to pull back. So that is the direction here. You good? Okay. So right now we simply write the equation here. If this is theta, then this is theta. Right? So that means the displacement here is how much? This displacement simply is, this is L2, this is L1. So this displacement equal to L2 times theta. And this displacement is L1 times theta. Okay, so basically this spring equal to K1 times L1 theta, and this one is K2 times L1 theta, and this spring force is K2 times L2 theta. Okay, so from this information, you should be able to write it out as strain energies that contributed from the three streams. And the strain energy from this spring, spiral spring, that is very straightforward. 1/2 times the K, this is KT2. Okay, KT2 times theta square. And the strain energy from this term is 1 times KT, 1 times theta square. So in total, you should be able to formulate 5 terms of the strain energy, and that is equal to this one. And this is similar to what we have done earlier. Okay. Can I leave the details to you? This one, we want to formulate the equivalent spring, and this is an elastic bar. So tell me first, this is the material 1, this is the material 2, and we know that this is a bar, and say E, A, L, A is a cross-sectional area, okay? We know the KEQ for a bar is equal to, I forgot, delta equal to FL over EA, and F divided by delta equal to EA over L, okay? So the KEQ is EA over L. We take up this template, okay? So for these systems, the original system basically is equal to, we have 2 elastic material, 1 and 2. Tell me they are in parallel or in serial connections. Parallel. Why? Because if we apply the force here, deform it, the 2 materials deform at the same amount. So they are in parallel. So that one is equivalent to this one. K1. K2, and this is rigid, and this is a force. Okay, you good? So therefore, in this way, what is KEQ for this one? So the KEQ for this system basically is equal to K1 plus K2. And what is K1? We simply take out this template. EA over L, we take out whatever the information from material 1, plus EA over L, we take whatever the information from material 2. That's it. Okay. So we have a few more examples here. Probably you can try to exercise.